Good morning. Let's start by reviewing what we did yesterday. I had a little summary of the first two lectures. So I started with some basic definitions when how to go from a Feynman integral to Feynman parameterization. I showed you some useful formula which uses dual coordinates, which I think is easy to remember. So whenever you ask somebody on the street what's the Feynman parameterization of a one-loop integral, you should be able to just write that down. It's very useful because whenever you have some integral and you just want to check some basic properties, you can just write down that formula and it's helpful. So whenever we need to go back to check something or to think about some properties of the functions at hand, that's very useful. And then I told you about some relatively standard techniques which have been developed in the 90s and 2000s, how to deal with Feynman integrals. So one idea is first to analyze identities by satisfied so-called integration by parts relations. So we derived how they appear, and I gave you a number of examples. These integration by parts relations then lead to the idea that for a given problem we only need to consider a certain set of so-called master integrals, finite set of master integrals. And we then proceeded to a set of differential equations for those master integrals. And in trying to solve them, we saw that certain generalizations of logarithms appear polylogarithms, or more generally, if we go higher in the epsilon expansion or in some more complicated examples, we saw generalizations of these, which are given by iterated integrals, not some random iterated integrals. Iterated integrals where we iterate only a small set of specific integration counts, which in our problem turned out to be actually only two of these, d log x and d log 1 plus x, as we saw when looking at the differential equation. And this particular set of iterated integrals is called harmonic polylogarithms. So I gave you the definition and some properties of these yesterday. More generally, what class of iterated integrals we'll discover or we'll meet will depend on the kinematical configuration of the Feynman integral, and sometimes also on the loop order. And so here are some of the original references, and so a lot of more useful information about background on Feynman integrals can be found in a book or series of books by Volodya Smirnov, lecture notes style, and these two lectures I gave, actually I was following some lecture notes which appeared in spring, so some lecture notes together with Jan. So if you want to, probably some more details which I didn't time to cover yesterday, but I was following closely these lecture notes. Just to reiterate somewhat, if you have a given physical problem, it shows an example of some one loop process which could occur. You have some quarks which interact with a gluon, there's some vector bosons. So some finite diagrams you need to think about. There's some amount of algebra involved, of course, here to identify what precise diagrams you need, but from the underlying Feynman integral, from the point of view of identifying what the Feynman integrals are, what's relevant really here is the kinematics. So I've kind of now simplified this and just, I don't care so much about the fact that this is a gluon, but let's just see what the propagator structure is. And so here I've written down the kinematics. In this case, consider the quarks on shell and massless as an approximation. Vector bosons massive. So then that's the kinematic setup that one needs to consider. And as we did yesterday, an important generalization is to consider such a Feynman diagonal for arbitrary integer powers A, which was, if you remember, which was what allowed us to derive integration by parts relations. And indeed, so that's the next step. We derive integration by parts relations. That tells us that there's a set of finite master integrals. In this problem, they look like this. There's some grading, some order of complexity by the number of propagators. So there's this finite set, and then one derives differential equations, as we did yesterday, to compute them. And in particular, when setting up the differential equation, it also becomes clear what the relevant class of functions is that one needs to describe them. So that's the general procedure within this method. Any questions on those points before we move on to the third lecture? Okay. Yes. So just right. I wanted to make two comments. First comment. So I was asked actually by several people, what happens if we, so here we're discussing arbitrary powers, arbitrary integer powers of the a's. What happens if there are some numerators? So I should have said, in fact, the a's are also allowed to be negative integers. So this way you can also describe numerators. It becomes more important actually at the higher root level, where numerators very naturally appear. So then you can use the same machinery, just considering that these values can also be negative sometimes to describe a numerator. And then a second remark is some technical but important detail about setting up, how to set up the differential equations in these on-shell kinematics. And the problem is that, in fact, if we think about on-shell scattering amplitudes, there are constraints, the momenta constraints. So just as an example, let's consider some massless four-particle scattering like this. Let's say for simplicity we have that all particles are massless, also the internal lines are massless, so we have these on-shell conditions. And in addition to that, we have momentum conservation. So the sum of the integral from 1 to 4 is 0 by momentum conservation. And what this means is that we cannot just naively differentiate the corresponding Feynman integral with respect to one of the momenta, because if we do it in a naive way, we will violate one of these constraints. So just to so what we want to do at the end of the day, we know that this object just depends on invariants S and T, like so. So that what we want to do is we want to differentiate with respect to S of T. But the Feynman integral that we can act with the derivatives on, it's expressed in terms of these momenta. And only after integration it's become obvious that we have that this integral only depends on S and T. So we need to somehow, the idea is we need to, by the chain rule, we need to act on the momenta and then thereby get a derivative with respect to S. But as I said, it's not so obvious because we need to be careful to satisfy those constraints. So as usual, when you have a system of constraints, maybe the most elegant way of dealing with this is to introduce some parameterization which automatically satisfies all the constraints. And well, maybe let me just give a very simple example. Imagine we have two variables x and y which satisfy x squared plus y squared equals 1. Clearly, so this only depends on one non-trivial variable, which we could, and we could solve this by introducing some angle. So then it would be there would be no problem differentiating with respect to that angle. But now we're in the situation that we want to differentiate with respect to x or y separately. So this is possible, but we have to make sure that we have some point on this circle satisfying this constraint. But if we differentiate, we stay on the surface of the constraint. So that is the problem. Now, as I said, one possibility would be to choose a parameterization, choose a convenient parameterization that removes the constraints, or that automatically satisfies the constraints. And this is not obvious, but in fact here this is possible. One could do this introducing so-called momentum twister variables. And these momentum twisters are in fact closely related to the dual coordinates we saw in the first lecture. So this is possible and very nice. I don't want to do it here because it's kind of deviates a little bit from the main goal of the lectures, but I just wanted to mention it. So instead, a second possibility is to choose a more pedestrian approach. Well, let's in fact first try to satisfy the first constraint. Let's just use that to eliminate P4. And so let me call this 1, 2. So we use equation 1 to eliminate P4. Whenever we see P4 in an equation, we replace it by minus the sum of the other three. And then we're left with the second constraint, which now reads P1 squared equals 0, P2 squared equals 0, P3 squared equals 0, and the sum of P1, P2, and P3 squared equals 0. So you see now, what we would like to do is we'd like to differentiate with respect to S. Say naively we could just take some derivative with respect to P1, which sees S but not T. But then if we do this naively, we will violate, for example, this constraint here. Because, so P1 squared equals 0, but if we just take a derivative with respect to P1, then we have twice vector P1, and that's in general non-zero. So we have to be a little bit more careful. Again, the same would happen if you started at some point on the circle here and you just differentiate with respect to x, which takes you away from this surface. So the pedestrian way of doing it is simply say, well, we want to define some differential operator with respect to P1. And well, so this is some vector. But we can contract it with some we have several possibilities of making a scalar operator. So let's make some ansatz. Let's make some ansatz like so. Let's say some parameter alpha times P1, beta P2, gamma P3. So let's consider this differential operator. Let me call it ds in fact. And well, what do we want to require? Well, we want to satisfy the constraints, so we want that ds acting on P1 squared on this constraint, on the surface of the constraint, is equal to 0. Right? So that, in other words, the differential operator commutes with the constraint equation. And likewise, we also have to watch out for this one, so we also wanted to commute this property here. And so I wrote this index here just to remind you that after differentiating we're allowed to use the constraint equation. So this we want, and then finally we want this to be a derivative with respect to S. So let's choose some normalization condition that the after S, then we want to find 1. So that it's indeed it will indeed be a partial derivative with respect to S. Okay, and so you can, of course, you can just set up these equations, and this will give you some solution for alpha, beta, and gamma. And this way, In this way, you've made sure that your differential operator is compatible with the constraint. So this is it's not quite as elegant, but it works fine. And so I just wanted to emphasize this point, because this could always lead to some problems. You could run into some inconsistencies if you don't take that into account. So now, before continuing, one thing that I forgot in terms of references. I told you that we saw yesterday that deriving this equivalence is rather simple. It amounts to some algebra, and after doing this a couple of times, it's probably nice to have some computer program which does that automatically for you. So there's some computer codes for deriving equivalents and handling them. One that I'm using myself is called Fire by Alexander Smirnov. I think actually a new version will appear very soon, so it's very up to date. I like it. It works in Mathematica. Always like Mathematica. Probably takes a little while to get used to it, but once you get used to it, it works very well. Another program which is public, which works very well, is called Reduce. I think there's a Z here. There's also something with C, but I think this is a Z. So this is by Alexander Smirnov, and this is by Andreas von Manschreuter and Cedric Students. So these are both very powerful programs, very useful. Oh, and very recently there's been also something called Lightspread by Roman Lee. So all of these are very useful, very powerful tools. I recommend all of them. Okay. Good. Any questions on this stuff with the constraints, differential operators? All happy with this? Good. So, let's see what I'm not saying. Very good. So now we already looked at some examples for differential equations. But now I want to move on to things that have been happening the last year. And in fact, last year I had a paper where I proposed some canonical form for differential equations, which kind of gives a guiding principle for what simplifications you can expect when dealing with them. So one of my goals today is to motivate and introduce this conjecture. Some conjecture for some canonical form of the differential equations. And this, how can one hope to get a canonical form? This involves using a freedom that we have. We saw it a little bit yesterday, using some appropriate basis for the master integrals. And so we'll talk about what we mean by appropriate. And I guess this conjecture on its own would probably not be so useful, but there's also a procedure for finding such a basis. So that's the second thing I would like to discuss, finding such a basis. So this will be my first two goals, and then once we've understood that, there'll be some further applications of this. So now, okay, so let's start with the first point. And in fact, to motivate this, I'd like to first say a few general things about differential equations, generalizing from the examples we had yesterday. So we'll assume that in some, we follow this, so we assume that we have some problem where we followed this strategy, so we identified some family of integrals we're interested in, we've arrived at a set of master integrals we want to compute. So let's start from there. So we have some set of master integrals, and we call them f. In general, they can depend on a number of dimensionless variables, s, t, m squared, and so on. So now, for the purpose of just for simplicity, for the moment, we'll restrict ourselves to one dimensionless variable, which we call x, and then the other dependence, of course, is on the dimension 4 minus 2x. And so later I'll tell you how this generalizes to the multivariable case. But for now, we'll imagine that there's one dimensionless variable that we're interested in. All right. And so again, just as yesterday, this is a vector with n components, where the number n depends on the problem under consideration. So yesterday, for the massive triangle, we saw that n was 3. We had the tadpole, the bubble, and the triangle. For other problems, this could be some bigger number. But as you'll see, it doesn't really matter what number it is. Okay. So now, as just as yesterday, then we set up some derivative with respect to that variable. So what do we obtain then? So if you remember yesterday, the important point was that whatever we get from differentiation, it will stay within the family of integrals that we consider. And there we have this notion of basis, so we can map that through some linear relation back to the integrals f. And so therefore, quite generally, we'll obtain some matrix here, which we call A, which can depend on x and epsilon, times the vector f again. So this is some matrix. If I n master integrals, this would be some n by n matrix. One can say a little bit more about the nature of this matrix. In particular, if you look at the way we derived IVP relations, you can convince yourself that this matrix will be rational in x and epsilon. So relatively simple. Well, if you look in more detail, there'll also be some hierarchical structure. If you remember yesterday, we saw that the derivatives of integrals of a certain number of propagators only involves the same types of integrals or integrals of less propagators. So there's some kind of hierarchical structure here as well. Okay, so we have this, and now the first thing I would like to focus on are the possible singularities of the integrals.
This matrix could be only polynomial in epsilon or not?
I think in general you will have a rational dependence in epsilon. However, if there are singularities with respect to epsilon, you might wonder whether or not they're spurious. Because, so, again, here we're treating, so epsilon basically means that we're talking about the dependence on the dimension. And, well, you can ask for a given Feynman integral, do you expect some singularity at a given dimension? So what would we naturally expect are some singularities at integer values of the dimension. If you think about Feynman parameterization, that's where you can have singularities that occur. So if you find some singularity at some tiny value of the dimension, you might wonder whether or not that is spurious. So I could imagine that you can prove some further statements about the epsilon dependency. In fact, this goes very much along in the same spirit as what we'll be discussing now for the singularity structure. So here first we'll focus on the x dependence, but many of the things we'll see, I think, will have an analog when you think about the epsilon dependence. So very good comment. But let's start with the x dependence. And so in general, if we have some function f, let's imagine f could have singularities for certain values of this kinematic parameter. So yesterday we had a function which had singularities at 0, -1 and infinity. More generally, let's say these singularities occur at some positions xi, and let's just assume there can be a finite number of them. And then we would like to study this differential equation in the limits where we approach one of the singularities. So let's, in fact, without loss of generality, let's just say there's a singularity at 0. Let's look at a singularity x going to 0. And then what's relevant is is how this matrix A behaves near 0. So there'll be some, we know the dependence is rational, so there'll be some leading term, 1 over x to the p, times some coefficient matrix, let's call it AT, epsilon, plus other terms. And the question is, what would be this leading power p here? What can we expect? Now, to understand this, let's for a moment consider the case of a scalar equation. So I remind you, we have a matrix, a system of equations here. But just imagine we had a scalar equation. Now, so I drop the vector on F. Well, let's just call it G, just not to get confused. Let's imagine we have such a function here. And we have such an equation. And well, here we can basically consider different cases for p. Well, if p is 0, then there's no singularity. That's fine. Then this would mean that actually we should remove this point from our list. What happens if p equals 1? Well, if p equals 1, then g, we can solve this. Then g would behave as x to the power a times some, well, in this case we've truncated the equation, we've just kept the most singular term, and in general there would be some other terms that follow. So that kind of behavior, that's actually something very reasonable. That's what we would expect from Feynman integrals. You can convince yourself of this if you look at the Feynman parameterization that we had in the first lecture, and looking at what happens if one of the variables gets small. This is precisely the kind of behavior one expects, some power law behavior. But now if you look instead at the case p equals 2 or higher, we see that one obtains a completely different kind of behavior. And so in that case, we find that the solution is e to the let's get this right, e to the minus a of x. Again, multiplied by that other time. And so you see, this is a completely different kind of behavior, and we would not expect this from Feynman diagrams in perturbative quantum field theory. I don't want to prove this here, but I think starting from Feynman parameterization, you could think of a proof of these statements. Perhaps people have already proved them. I would think that these are properties that people would have considered in the 50s or 60s when studying rate behavior. But anyway, here I just want to take from this discussion that it's reasonable to assume that we have that this is the behavior that we expect for Feynman diagrams. So we have a set of singularities, and we would expect them to be of that type. But now, of course, here we consider the scalar equation, and things are more complicated in general because we have a matrix equation here. And what this means is that actually, even though we expect this behavior, we expect the highest powers of the terms just to be 1, it can happen that you have some terms in the matrices which have higher powers, and so which look like you have divergences of this kind, but in fact they turn out to be spurious. So there can be spurious divergences. Just as an example, let's imagine we have some equation with the following type. I hope this goes well, because I was just assembling this example 5 minutes ago, so I hope it won't be too wrong. But let's assume we have some matrix like so. So let's say we have some nice terms on the diagonal, which you know, like we had yesterday of power 1. But now let me add some bad off-diagonal term like so. And list on 2x2 system. So then this term would be unexpected. But now, by the fact that we have a matrix equation, we could hope to eliminate this term. And in fact, how to do this? We could say let's do a change of basis. Let's say f equals some transformation matrix times a new basis t times a new basis g. Well. Let's in fact do this more generally. If this matrix is called A, then so we just plug this in. What will happen is that actually this is like a gauge transformation. We'll see presently why I call it this way. But just plugging this in, we can compute what we will get again an equation of this type of the new matrix A. And well, the new matrix A, in fact, it's given by the following. So T inverse of A times T minus T inverse derivative of T. Just by using the chain rule, we get this new. So let's call this. Call it A prime. And so then we have a new equation, dx g equals A prime times g. So you see, what this means is that this notion of the degree of the singularity that we have here, it's only valid up to such gauge transformation. So what we would like to do is we would like to define, if we want to define the true degree of the singularity, we have to the statement has to be that does a basis exist where we have this minimal degree? So as you can see, there could be some basis where we have, it looks like we have degree 2, but it could be that we can transform this away using some gauge transformation T, such that the true degree of the singularity becomes apparent. So this is not obvious. Now, okay, now let's see if I did my homework correctly, we should be able to reduce this degree of the singularity. In fact, so I've constructed this example in a special way that this unwanted term, this is off diagonal, and moreover, if you look at this unwanted, let's look at this unwanted term. You can see that this matrix is nilpotent. And this is not the case in general, but here it's useful. And often when this is so, we should try to construct a gauge transformation, which is the following. Let's take this one, and T inverse is just this, thanks to this property here, nilpotency. And now we can easily compute what A prime is. And well, if I did my homework correctly, this should just remove the unwanted singularity.
And it's more simple to conjugate by the matrix 1x, diagonal matrix 1x. So,
Are you proposing a different way of removing the singularity?
yes, it can simply give the simple 1 over x square and make
Well, I don't know off the top of my head, but one would have to check. So I think this will work, but maybe there are other ways of doing it. I mean, in general, there's always a huge degree of freedom using this gauge transformation. The only requirement of T